Hi, my name is Shrutidhara. I am working as an assistant professor of mechanical engineering at Indian Institute of Technology, Jodhpur. And I'll be presenting one of the recent work that has been going on in our lab. So, assistive technology is the technology that kinds of assists individuals which have restricted mobility. So people who cannot really move. And that can come because of series of reasons. It could be because of stroke or paralysis or maybe spinal cord injuries. So this technologies enables these individuals to have some control over their immediate environment and also regain some sense of independence. So they do not have to depend on another user to use them. For example, to switch on and off a light, or maybe close the door or open it, or maybe send an emergency alert in case there is an emergency happening, something like that. So touch sensing is one of the key technology which has been used in assistive devices for long, simply because they are simple to use, because you can simply touch and it will convert the human touch into digital signals. They require minimal effort, and you can also customize them into different designs. But they can come in various technologies, like it could be capacitive sensors or resistive or piezoresistive or triboelectric, all of them. But all of them come with challenges, because although they have been developed mostly for rigid surfaces, they do not give consistent output if they're used on curved surfaces. And especially that's because when you flex a sensor, it disrupts the stability or it diminishes the sensitivity. And especially if the environment is dynamic, that means you're continuously bending and flexing, that you may not get a consistent output, which is why it is challenging to integrate them on curved or irregular surfaces. And also, most of the work that we come across, we see only one or two sensors being used. People do that so that they can minimize the fabrication cost, or maybe reduce the noise, and also to minimize the complexity in wiring and these things. But if you use multi-element sensing arrays, things are that you can have high spatial resolution, and if you can somehow overcome the noise and maybe do something to reduce the fabrication complexity. And the devices that we come across are, of course, very expensive. And when we want them to be accessible to people with limited resource setting, like in country like India, not everybody can afford such a device. So if you want it to be really simple and really inexpensive, then we have to come up with something that is really, maybe use and throw type. So our solution is we offered a very simple touch sensitive panel using a multi-element sensing array. And it looks like just like a wristband. It's stable enough, and it works like a device. So you can touch on anywhere on the panel. But just by touching or making different gestures, you can control different devices, like the switching on of a light, or closing or opening a door. So the first step was to fabricate the sensing patch. On the right-hand side, you can see the sensing patch that we have developed. This black colored flower-like lines, the petals, those are the sensing elements, and there are multiple elements. This helps us because now it can detect touch from all the directions anywhere on the patch. And secondly, even if one or two sensors fail, the patch will still be functional. It will not just like go waste. The silver connecting wires, you can see this one. These are printed using highly conducting silver ink. And all of this, it is basically actually is a strain sensor. So if you bend it, there is the carbon nanoparticles which are making this sensing lines. They will just move apart, and then you will see a change in resistance. That basically is the working principle. So you bend it, the nanoparticles move apart, the resistance shoots up, you leave it, they come back again, the resistance comes down. The substrate on which this is printed is a flexible PET substrate. We call it Melinex. And the design is, of course, customizable, just like I told you before. So initially, the patch that we made is strain sensitive, and you can see here that if you bend it, it will reflect in a change of the resistance. So how do we make it touch sensitive? It was very simple. We just added a foam layer. And because the foam layer is porous in nature, what it allows us is to localize deformation. So now if you touch somewhere, that touch is converted into localized strain, and then the sensor becomes touch sensitive. So now if you tap on a particular point, I have just included this 3D graph just for visualization purpose. And you can see where the sensing element, the resistance is changing, and accordingly you can detect different taps, swipes, single finger, double finger tap, like that. Once we made the patch, of course, we have to now calibrate them. So we calibrated for pressure sensitivity. Here you can see we have done the pressure sensitivity calibration both on curved as well as on flat surfaces. And you can see there has been a slight drop, but that is not really very high. So the sensitivity is 0.82 in case of flat, and it reduces to obviously 0.73 when you curve it to an extreme radius of curvature. The response time is really, really fast. It's only 180 milliseconds, so it's kind of an instant. And the repeatability is excellent. We studied it here. I have shown until 1000, but we have tested up to 7000 cycles, and the drift is really, really less. You can see that it's almost repeatable. So now we got the thing that it works both on the flat as well as curved conditions. The repeatability is extremely nice. So now we are good to go. We have to now build up the evaluation electronics. So here is the evaluation electronics. That is the spring-loaded components. So this is the end of the sensor. If you remember sensing patch, this just goes there. All you have to do is click on it, and then you're set. This is the piece of microcontroller we are using to read the output of the sensor, and this is the ESP32 we are including because we are also integrating ML into this work. So the entire system basically works on 1.75 volts, and the entire inference time. Inference means just from the point of touch to reading what kind of touch is it, and then to controlling the device, it takes only 180.6 milliseconds. So because now when we make a gesture on that patch, we have to also predict what kind of touch it is. Is it a single finger touch? Is it a swipe? Is it a two finger touch? Is it a tap and hold? So all of that is done using this on-device ML. So we have used on-device ML using the ESP32 I have shown. And we use only CNN model because that's the most appropriate one for on-device ML at the moment. So the data set is we have trained with 6,000 data points into 6 different classes. Here are the 6 different classes from 0 to 5. You can see top touch, bottom touch, left, right, and no touch, and two finger touch. And then combine those touch to detect swipe. So if it is 0 and 1, that means if the system detects a top touch first and then a bottom touch, then it automatically takes the downward swipe, or vice versa, upward swipe and so forth. So here you can see this is again just a 3D image showing you that it has detected a single finger tap. And this is a confusion matrix, which shows the accuracy of our model, which is really high. After 5-fold cross validation, it's about 98%. So this is the system you can see here that we have developed. The very simple, just a very normal wristband structure touch panel, and you can touch depending on where you are touching on the location and what kind of touch is it, single or double. You can use a external device like controlling a keyboard or switching on and off a light like that. So we can classify single and double finger taps, and this is portable. Of course, you can see it's very, very cost effective because we have used fabricated using screen printing. So you can make as many sensors as you want, and you can take any number of design. Till now, we are handling 15 sensors at a time, but we also intend to go ahead with more sensors if required in the future. So here is the assistive living tool, the first one, light control. You can see here. Once the system detects a tap on anywhere on the sensing patch, then using this MOSFET, it sends the power 24 volt to the light, and the light will glow in full brightness. You make another tap, then it reduces the voltage by half, and the brightness of the light will become less. If you make another tap, then it will simply switch off the light. So this is the first tool. The second tool is here, controlling the door. Here we have used the solenoid lock. You can see here, if you make an upward swipe, just like the person is doing there, then the latch just comes out and it locks the door. And if you make a downward swipe, then the system reads, detects the gesture, and it unlocks the door because the latch just goes in. And that is done using this relay model here. The third one is this wireless emergency alert. Here, if you tap and hold with 2 fingers anywhere on the patch, then what happens is this is connected to the internet using the mobile hotspot, And we have already stored the emergency mobile number and the message. Maybe let's say the message is like the patient requires help. And if we have the emergency mobile number stored, and then if the person just tap and holds with 2 fingers, then it will directly send an emergency alert system. So this is overall to the key takeaways is that we have developed this flexible touch sensing patch, which is highly sensitive and has very high response time. And we are able to recognize different gestures in using this multi-element touch panel and with the help of integrated on-device panel. And based on these gestures, we are able to control outside devices like a light, a door, or send an SOS messages. So this kind of sensors or devices have transformative potentials for people with restricted mobility and especially for people with resource limited settings and like in countries like India, where not everyone can afford an assistive device. And because the design is very, very simple, it is just like a wristband structure. So it will work on the go, or you can just place it anywhere on a wheelchair handle or on the bedside, and any of the person can use it. So thank you very much. There are questions.